Questions about anything from last time? Well, today's a really interesting subject that will show you the power of some of the tools we've been learning. I'm going to answer this famous question using things we know about Fourier series, even though it's a fact about the Fourier transform. It's a it's a mind-blowing, important thing in physics. The physicists, the Heisenberg uncertainty principle is a fact about subatomic particles, that there's something about quantum mechanics that means that you can't know exactly the position and momentum of a particle with precision. So you've got to settle for one or the other. You can't have both exactly. And because physicists use Fourier transform in the study of quantum mechanics, and when they formulate that mathematically, it boils down to the statement that a function and its Fourier transform can't both have compact support. You got to study quantum mechanics to get that connection, but that's what it turns out to be mathematically. So that's the version I'm going to deal with today, and I won't worry about the physics connection. It's kind of an advanced subject. But the math is straightforward for us, since we know quite a bit about Fourier series at this point. So let me remind you what some of these words mean. The support of F that's written usually SUPP for support of F, and that's the closure of the set where F is not equal to 0. Let me see. Closure of the set of points X where F is not equal to 0. F of X is unequal to 0. And you could write that in set theory notation as the set of X where F is not equal to 0, and then the symbol for the topological closure of a set is overline. Well, that's always being the closure of something. It's a closed set. Sup F equal the closure of something means it's going to be closed no matter what. And compact means it's closed and bounded. So basically, this just means that the set where F is not equal to 0 is bounded. So compact in R is equivalent to closed and bounded. So the big deal is that the boundedness thing. And I shouldn't, if you haven't seen these facts about topology before, a closure of a set S contained in the real line is S together with all its limit points. Okay, that's the closure. So let's see, what would the soup look like? A compact support means that it's zero outside of some set, and then it wiggles around. And so the set where it's not equal to zero would be this red stuff with a hole right there. And it would there'd be a hole right here too. But when you make the closure, then you'd fill in those holes. So you'd fill in these black spots here. And so the soup would be that red stuff and throwing in the closure would throw in the holes. And the fact that that's bounded is basically means compact support. So this picture here, f of x with compact support. And that set there is the support of f. Questions about that? Let's see. Well, here's some examples of the closure of a set. Let's see, if I take a set like 0, 1, with 0 in but 1 out, then the closure of that set would just toss in the point 1 that's missing. That's a limit point. And you toss that in, that's what you get. If you take the rational numbers, they're dense among the real numbers. And so every point of the real numbers is a limit point of rational numbers. That means when you take Q and toss in all the limit points, you get the closure is all of R. And if you look at Z, the integers in the real line, of course, those things are isolated. They don't have any limit points. And so when you take the closure of the integers in the real numbers, you don't add anything. Nothing gets added. So that gives you a feeling for what that means. Another topological fact I'm kind of maybe assuming you have heard about in Math 341 is that S is closed as a set if and only if its complement is open. So R minus S is an open set. An open set is one that has a little open interval about every point that's in the set. Okay, so here's the proof. Let's suppose I think I'll do it for a C1 smooth function first. So let's suppose F is C1 smooth with compact support. Then F and its Fourier transform and F hat cannot. Then the F hat can't have compact support. So I was saying they can't both have compact support. So F has compact support, and F hat can't have compact support. well, I guess it could be identically 0, so I should say unless f is identically 0. That's the only time. So that's the fact. Let me now show you. It's going to be rather simple, or not simple, but it's going to use easy facts that we know. So let's do the case. Let's say the support is contained in minus pi pi. So let's suppose that it's in minus pi pi. And I'm assuming f is C1 smooth. So let's see what the Fourier transform is f hat of s equals, I like put my square root of 2 pi in front. Of f of x, it's the integral from minus infinity to infinity of f of x e to the minus I s x. And of course that integral exists because f has compact support, and everything in there is nice and smooth and integrable. So no problem. That exists. And you stare at that for a minute and realize, that reminds me of Fourier series. And in fact, so now I'm thinking out loud, because the support of f is in the interval from minus pi to pi, that's the integral. I throw away the integral part that's 0, so that would be the integral from minus pi to pi. And if the Fourier transform had compact support, then this would be equal to 0. So this would be equal to 0 if s was bigger than something. Say bigger than m. If f has compact support. If f hat has compact support. Oops, what happened to my I? ISX. Well, there's a lot of integers out there. And so the aha moment, we would see that the Fourier coefficients are equal to 0. We would see that the Fourier coefficients, series coefficients, let's see, what are those series? Those would be Cn. Those are equal to 1 over 2 pi integral from minus pi to pi. F of x, same thing, except in place of an s, we'd have an e to the n. E to the minus I nx dx. Our 0 when the absolute value of n is greater than that m. That's weird. That means the Fourier series for f is a finite thing. And the Fourier series converges to, so the Fourier series is a trig polynomial. Let's see, so the Fourier series for f on the interval from minus pi to pi is a trig polynomial. And that's weird. And that's going to be the key to understanding this. And let's see, we know because f is C1, the Fourier series for f converges to f. C1 smooth, the Fourier series for f converges to f. On the interval from minus pi to pi, at least. It might not, well, yeah, it's 0 at the endpoint, so it actually converges at the endpoints too. So the Fourier series for f converges to f on that interval. So what we have is that f of x would be a sum of absolute n less than or equal to m of the Fourier coefficients e to the I nx, a trig polynomial. How in the heck is it possible for a trig polynomial? Here's the picture. So let's see. Here's let's take minus pi plus pi. My f has compact support in that interval. That's what I'm assuming. So the graph of f, and it's C1 smooth, so it's differentiable. It would be 0, and then it could wiggle around a bit. I'm going to make it smooth looking. Let's see. There, it's going to be coming in here. Then it could have a couple wiggles, and then it's got to go out and be smooth again like that. But I'm only going to care about what it looks like inside the interval from minus pi to pi. All right, so here's the weird thing. I've got f as a trig polynomial. And here's f right here, this blue stuff. And what's bugging me here is that, look at, there's a spot over here where f is identically 0 in a neighborhood of x naught. So what I see there is a trig polynomial that is identically 0 in a neighborhood of x naught. So that's too weird. How would that be possible? I have a trig polynomial identically 0 in an interval x naught minus something small to x naught plus something small. There'd be one on the other side near pi also, where I could do that. Well, that would imply that trig polynomial is identically 0. So I claim this will imply that the trig polynomial is identically 0. It's the 0 polynomial. On minus pi pi. And that implies that f is actually identically 0. On minus pi pi. And that means f is identically 0 because it's 0 outside. The support was in minus pi to pi. So we know it's 0 outside there. And so f is identically 0 on R. And that's what we wanted to see. That the only way we could get the Fourier transform to have compact support would be if f was identically 0. So that will be the end of it. Okay, and the key is trig polynomials are sums of cosines and sines. And cosines and sines have power series. And so if you think about this, is a famous fact that if you have a power series, it's given by Taylor's formula. So if it's identically 0 in the neighborhood of x naught, all the Taylor coefficients would be 0 at x naught. And the radii of convergence of those series is infinite. So that means the Taylor series is the 0 Taylor series. That's how we're going to do it. So this is a Taylor series fact. Let's see. So let me think about my trig polynomial. The key is going to be a Taylor series fact. And let's see. I've got my trig polynomial. F of x is equal to a sum of finitely many terms, Cn e to the I n x. And that would be a sum, let's see, that's a sum of, let's see, the Cn would be an plus I times bn. And the e to the I nx is cosine nx plus I sine bx. And so let's assume that f of x is a real valued function. And then I could expand this and get, let's see, what would the real parts be? The real parts would be an times the cosine term would be real. I times I would give me minus bn times the sine nx. That's the real part. And then I'd get an imaginary part, which I don't care about. So who cares? Because that left-hand side is real. And so whatever it is, that's going to add up to 0. That must equal 0 because the left-hand side is real. And we see that this must equal the f of x. Okay. And that, of course, that's only true on minus pi to pi. But cosine and sine have a Taylor series that has an infinite radius of convergence. Cosine and sine. Well, you know the ones at 0. You know by heart cosine t or cosine x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. minus dot dot dot. And sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. And they also have so those are famous series, and the radius of convergence are both infinite. So they converge for all x. And so I'm thinking out loud now. Cosine nx, sine nx have Taylor series expansions, or power series expansions. About x naught. Also with radius of convergence equal to infinity. And so what we see is that f of x is equal to that trig polynomial on minus pi pi, and that trig polynomial is a summation of, as n goes from 0 to infinity, of Taylor coefficients, a, b, c, what's my next letter? E. I'll make it capital A. Capital A sub n, x minus x naught to the n. So this has an infinite radius of convergence. Radius of convergence is infinite. And this is a true fact on minus pi to pi. Okay. And Taylor's formula for the coefficients an is the nth derivative of f at x naught divided by n factorial. And those are all 0 because f is identically 0 in a neighborhood of z naught. Those are equal to 0 for all n. And that means f is identically 0 and we're done. And it's 0, f is identically 0 on that interval. Questions about that? It's kind of a simple thing to figure out. And we're done. That's the demonstration of the Heisenberg uncertainty principle. I'd use minus pi to pi just to make my life easier, but not if the next case would be the support would be of f contained in, how about minus LL? Then you use Fourier series that we've developed for that interval. So we know Fourier series on minus LL f of x would be a sum from minus infinity to infinity of Cn e to the I. Remember, it's n pi x over L. Where, remember those coefficients, Cn would be 1 over 2L integral from minus L to L f of x e to the minus I n pi x over L dx. And we see the Fourier transform there again. That would be equal to 1 over 2L. Because f has compact support, that'd be the same as this integral. And so if that thing inside the integral is, let's see, so we would see that's equal to 0 if n pi x over, if n pi over L is bigger than m. Where the support of f hat is assumed to be in minus m to m. Or I should say when. So the exact same argument works. So the argument is exactly the same. You just have to put an L where the pi's are. Questions about that? That's kind of nifty. I want to now show you that so here's an improved version. Let's say I assumed f was C1. I can actually assume something less. I can assume f has compact support, and it's merely piecewise continuous. So I can assume it's merely piecewise and continuous and has compact support. The sticking point that we got to think about, and that we have thought about. So the sticking point, the Fourier series for f is going to look like it's a trig polynomial, but if it's not piecewise C1, we don't know that the Fourier series converges. So the sticking point, the Fourier series for f is a trig polynomial, a finite sum. Does that mean that f is a trig polynomial? Must f equal a trig polynomial on the interval from minus pi to pi? The answer turns out to be yes, and we've kind of thought about this before. Let's see, why is that? Want to think about it for a second? If you think about some stuff we know, let's recall. Let's suppose we went through this once. Suppose f is piecewise continuous, so it can have jumps, etc. It's piecewise continuous. If the Fourier series, if all the Fourier coefficients are 0, then remember f had to be 0 where it was continuous. And so those were written f hat n equals 0 for all n. Then f had to be 0 wherever it was continuous. At continuous points. At points x, where f is continuous. And remember how we showed that. We used Parsifals. So we had Parseval's identity when f was merely piecewise continuous. And Parseval's told us that, what does it say? The sum of f hat of n squared from minus infinity to infinity is equal to, what goes here? Is it 1 over 2 pi or 1 over pi? Anybody got the formula in front of them? It's 1 over 2 pi, isn't it? I'll fix it later if it's not. Doesn't really matter what it is, because if all those coefficients are 0, this would be identically 0, a sum of zeros, and that would mean that integral would be 0. And if f has any points where it's continuous and not 0, that integral would be strictly too big. This would be strictly positive if f of x is unequal to 0 at a continuous point. Okay, and so that can't happen. That means that f has to be, and so f is piecewise continuous. That means if it's continuous, it has to be 0, and where it's not 0 would be just finitely many points. So, it would be 0, and then maybe it'd be 0 for a while, and then it might be so that yes, that's what the f would have to look like. Wherever it's continuous, it has to be 0. And so there's isolated points where who cares what it is. But it doesn't have to be 0 at those weird points. But it means you might as well make it 0 at those weird points. So I know that fact. And you sit around and think about what you would do in this trig polynomial case. And after you think about it for a while, so the Fourier series for f, let's assume it's a trig polynomial. Equals a trig polynomial. That would be a sum as absolute n is less than or equal to n of coefficients a n e to the I n x. And I know this fact above. So that's not an aha moment. This is the aha moment. The Fourier series for f minus that trig polynomial remember, Fourier coefficients are linear. So if I subtract the trig polynomial that's the Fourier series, then I'm going to get something that has 0, the Fourier series. So the Fourier series for this are all 0 terms. Is the 0 series, the 0 Fourier series. And so I can apply that thing, a previous thing. If the Fourier series is 0, then the function has to be 0 where it's continuous. Okay, and so I drew that picture there. It means that my f had some weird values that you can just fix. So what we see that f is equal to this trig polynomial, except at maybe finitely many points. And so you can just fix it there. except maybe at finitely many points. Just change the values of those finitely many points. So in fact, there are finitely many isolated points. Change the values there. It doesn't change any of the Fourier coefficients or anything else. Change the values there to make them match. And so now we have that f as a trig polynomial, and we can do that power series argument. And so the whole thing goes through after that. Let's see. Didn't expect to get done so fast. Don't think I skipped anything. Questions about anything? Let's see, so you might remember I like to do Fayers, and I showed Fayers implied Parseval's, and that implied uniqueness of Fourier coefficients. Whereas Stein did Fayers, and then he made a good kernel. So he showed Fayers implies uniqueness of Fourier series. Of the Fourier coefficient. And let's see. He did this by making a good kernel out of Taylor. Let's see. He made a good kernel out of trig polynomials using Fayers. And then he showed Parseval's. So I prefer my way of looking at it. But I think the reason Stein did it that way is because he wanted to demonstrate the whole business about good kernels, because he was going to use it in the coming chapters. And we're still using it. So it's not a waste of time, but it's I found my way speedier and easier. Anyway, if you notice that, that's what happened. I feel like I'm done for today. It's hot in here. Is it hot back there? Something's happening up here. This thing is making noise and it's hot. I don't know if it's heating up the whole room. Okay, I guess we'll call it quits then for today, unless there's questions about anything. Or any questions about the homework? Yeah.
I had a question about something in the proof. I was wondering why we can say that that f of x is identically 0 on an interval around x0.
Yeah. Because the support is a closed and bounded thing. And so if it's in an open interval, it can't be all the way out to the pi, minus pi there. There has to be the minimum. Oh, yeah, okay, so that's a good point. I'm glad you're asking me that. So where's the picture? Back here. Okay, the support of F is contained in minus open interval. And that support of F is a closed and bounded set. So it has a max and a min. So let's see. Let M be the minimum. So let M equal the min of X such that it's in the support. That's a closed set. And so, in fact, that M is going to be over here somewhere. The M can't be minus pi. So remember, a continuous function, the identity function is a continuous function on that compact set. So it has a minimum. And the minimum isn't minus pi. That minimum would be attained. Okay, and so it must be true that minus pi is strictly less than m. Does that answer your question?
Yeah.
Yeah, because, I mean, you can think about x is a continuous function on that set, and so its minimum would be attained, and it's not minus pi, because the function is 0 at minus pi. Okay. That's the reason you can get it. So you can get an interval where it's identically 0 in a little minus delta plus delta kind of thing. Okay. That's enough for today.
For the Wales material, I was looking at a lot of texts that do it from 0 to 1. Is there a reason we're doing it like on the
just because we've been doing Fourier series.
From minus 5.
Right, so it doesn't matter. And if you know it on 0, 1, if you do it on 0, 1, then you know it on anything else. Yeah.
Okay.
It's probably a math thing to be minus pi to pi, and a CS thing to be 0 to 1.
I have a question on the third question from the homework.
Uh-huh.
So we have to show that the integral from delta to infinity of phi t of x tends to 0 as t goes to 0.
Yeah.
And I have it at this point where it's the same as the integral of delta over t to infinity of phi of x. And I was wondering if it's an okay argument just to say that since this bound down here goes to infinity as t goes to 0.
Well, you can actually calculate that, right? You're going to compare it to something you know.
Yeah.
But you can compare it to e to the minus absolute u.
Oh, okay,
so,
yeah.
I mean, just like you did, yeah.
And that
Then you can actually